Okay, I thought I could also make a short video on the idea of pH versus pKa. So the idea here, and I want to really simplify it, is that the pKa value is an intrinsic value to the molecule that you are describing, or the functional group that you're describing. So for example, this carboxyl group over here has a pKa of 2.0. The NH3 group has a pKa of 9.5. The thiol group has a pKa of 8.2. So it's specific to whatever functional group you are looking at. And just because you have two carboxyl groups doesn't mean it has the same pKa. So the pKa can vary based on other factors, which is outside of the scope of this class, such as like the charge of the atom, resonance effects, inductive effects, orbital effects, stuff like that, but that's OChem more. So we're going to give you always the pKa's, but I want you guys to understand that the pKa's are specific to the molecule being shown. Okay? And the idea of the pH now is the pH is the environment. So another way of looking at it is, for example, if I drew out this cup of water right over here, okay? So what we can do in this cup is we can change the pH, okay? And all that means is that we're changing the concentration of freely floating H3O plus ions, okay? So what's happening, so to simplify everything that I just said, when you're looking at your pKa, that is specific to your molecule. In this case would be our amino acids. So I'm just going to put molecule amino acid. Okay. And then the pH is your environment, which in this case would be your solution. Okay. And another thing that I should point out is the pKa, it's the point at which you're going to get a 50-50 mix of your weak acid to conjugate base. So at a pKa of 2.0, if your pH equal to that pKa, you would see that inside that solution, you would get 50% of your weak acid and then 50% of your conjugate base. Oh no, that is not good. Okay, and again, the same thing would happen if you then switch the pH to 9.5. That would equal to the pK of the amino group, and you get a 50-50 mix of the NH3 plus to the NH2. But okay, so pK is the molecule, pH is the environment. So now let's see if we can use this idea to say, if I'm at a specific pH, how do I know if my amino acid will be protonated or deprotonated? Okay, so this is like a shorthand way of using the Henderson-Hasselbalch equation. If your pH is within 1 unit of your pKa, I would recommend using your Henderson-Hasselbalch equation. But if you're more than 1 pKa unit or 1 pH unit away from your pKa, effectively, like if you're 2 or 3 pH units away, that means you're gonna have a 100-to-1 or a 1,000-to-1 ratio. So you can effectively say you only have one species. You can use this trick that I'm about to show you in order to determine if your functional group will be protonated or deprotonated. So let's see what I mean. Okay, so let's just say that, okay, we're gonna look at the same amino acid cysteine right over here, and we're gonna look at the same, and we're gonna be adjusting the pH in our solution to see what happens. Okay, so all we're gonna be doing is, let's just look at this amino acid right now, and instead we're gonna make the pH, let's say 4.5. Okay, if I make my pH 4.5 and I look around at all of the functional groups of the pKa's, it's more than 1 unit away from my pKa, so I can use this trick. Okay, so the way I'm going to do it is I'm just going to write out the pKa's next to each pH. So we're going to kind of look at it like this. So pKa, which again refers to the molecule, is equal to 2.0, and then the pH, which is equal to the solution, is equal to, and this is for the COO minus group or the carboxyl group, pKa's, and then the pH of the solution is 4.5. So now what I'm going to do is I'm going to look at it kind of like weightlifters or a tug of war. So what's happening in my solution is that the protons are freely floating around at this specific pH, and you can think of them effectively like bodybuilders, okay? So whichever one has the bigger number, okay, that one is like the stronger one. They can wrestle away the proton from the other molecule, okay? So for example, if we're talking about these two in this situation, which one has the bigger number? Which one's stronger? In this case, the pH or the solution is stronger, meaning that it'll wrestle away the proton from our carboxyl group, so that at a pH of at a pH of 4.5, we can say that our carboxyl group will be deprotonated. And this makes sense, right? Because we're at a pH greater than our pK. Now let's do the same thing for comparing the other functional groups. So now let's say our pK is 8.2 and our pH is still 4.5. So now we're looking at if our thiol group is going to be protonated or deprotonated. And what I'm going to do over here is I'm going to compare the two. The pKa now in this case is bigger, meaning that this one is going to win out. So that means that in our solution predominantly, we're going to see the thiol group remain protonated because the molecule is stronger and it'll keep its proton, okay? And in this case, what it means is that the pKa is larger than your pH, okay? Now what we're going to do is we're going to now do it for the amino group, and pKa is equal to 9.5, and we're going to compare it to the pH of 4.5. And again, because the pK is bigger, that means that your molecule wins out. So that means that you're going to predominantly see this happening, okay? So the key takeaway I want you guys to take away from this is that whenever your pH is greater than your pKa, your solution wins out and it takes the proton. But if your pH is less than your pKa, meaning your pK is larger than your pH, your molecule or your functional group, your amino acid will win out and it'll keep that proton. So for these kind of problems, if it's asking you what's protonated and what's deprotonated, all you have to do is compare the pKa, which is intrinsic to your molecule, and compare it to your pH, which is the environment, which is the thing that you're adjusting, and you're going to see what can stay protonated and deprotonated. And I really want to emphasize this, that this trick only works whenever you're more than 1 pH unit away from your pKa. Because whenever you get closer and closer to your pKa, you're going to get closer and closer to that range where it's going to be a 50-50 mix of your weak acid to conjugate base. So then it won't be as clear, and you're going to have to use the Henderson-Hasselbalch equation to get the actual ratio of your weak acid to conjugate base in those situations.